Having positioned activity A on our diagram, we can observe from our precedence table that it must immediately precede activity D. We can therefore draw an arc representing activity D immediately after the arc representing activity A on our diagram. In a similar way, we can draw the arc for E immediately after the arc for B. After this, we notice that activity F must be preceded by both activity D and by activity E. We can represent this by joining D and E together at a single node, with activity F following. Activity G also follows after activities D and E, and can therefore be drawn after the same node. H follows F, I follows G, and J is preceded by C, H and I, so these join together at a node preceding J. Finally, we note that J does not appear in the column of preceding activities. Since there is no activity which J precedes, it must be at the end of the project. In a critical path diagram, all activities must lead to another activity or the end of the project. The next step is to determine how early we can start each of the activities. Here, each activity has been labelled with its duration. We are going to write the earliest and latest possible start times for each activity in separate boxes. The left-hand box is going to show the earliest time that we can be at a particular point in the project, and the right-hand box is going to show the latest time. Taking the start of the project as time 0, we can fill in the first earliest start time box at the start of the project. The earliest possible time for the end of A is obviously 0 plus 10. That is, the earliest time at which it could have started plus the time it takes. Similarly, 0 plus 9 for the end of B. However, when we reach the node at the end of activities D and E, we are faced with a choice. 10 plus 2 equals 12, or 9 plus 4 equals 13. Since we are looking for earliest possible start times, it might at first seem right to pick the smallest value of these, 12. However, we must bear in mind that we can't start activities F and G until all of the required activities beforehand have been completed. We won't have completed all of the preceding activities until 13 weeks. In other words, when faced with a choice, we pick the larger value. Continuing, 13 plus 1 is 14. And again, 13 plus 1 is 14. At the beginning of J, we have another choice, this time of 3 possibilities. 14 plus 3 is 17. 14 plus 2 is 16. Or with activity C from the start, 0 plus 3 is 3. Remembering to pick the largest of these values, 17, since activity J cannot be started until everything which must precede it has been completed, we write 17 in the earliest start time box. Finally, 17 plus 1 is 18, so we see that the fastest possible time in which the project can be completed is 18 weeks. The next step is to consider the latest possible time that we can be at any stage of the project, whilst still managing to complete the entire project on time. Assuming that we wish to complete the project in its fastest possible time of 18 weeks, the latest possible time that we would like J to finish at is therefore 18 weeks. In a reversal of the logic which we used in going from left to right to find the earliest possible times, we are going to go from right to left to find the latest times. This time, when faced with a choice of different possible values, we will always pick the smaller value. So 18 minus 1 is 17. 17 minus 3 is 14. 17 minus 2 is 15. And now we are faced with a choice. From activity F, 14 minus 1 is 13, or from activity G, 15 minus 1 is 14. Remember, going from left to right to find the latest times, we always pick the smaller value, which is 13 in this case. Thirteen minus 2 is 11. 13 minus 4 is 9. And once again we are faced with a choice. From A, 12 minus 10 is 2. From B, 9 minus 9 is 0. And from C, 17 minus 3 is 14. Once again we pick the smallest of these, which is 0. In fact, if the procedure is done correctly, we should always come back to 0 at the start of the project. There are a number of points in our critical path diagram where the earliest and latest times are the same. These have been shown in green here. Now, looking at the point on the diagram at the end of activity A and at the start of activity D, we see that the two times are different, 10 and 12. This means that activity D could start as early as 10 weeks, but it could still start as late as 12 weeks without delaying the entire project. There is 2 weeks spare time or float. Similarly, it would be possible to start activity I as early as 14 weeks, but it's not necessary to start it until 15 weeks for the project to be completed on time. At other points in the diagram, the two times are the same. Any delays to activities at these points will cause the whole project to be delayed. The critical path is the chain of activities which pass through these nodes. Any delay to these critical activities will cause the whole project to be delayed. The critical path then is B, E, F, H, J. These activities must be completed on time or the whole project will run late. We mentioned float. There are a number of different types of float defined. Consider an event to be the start or end of an activity. Then, for an activity ij, which starts at point I and ends at point j, then the total float is defined as the latest time for event j minus the earliest time for event I minus the duration of the activity. In the example shown here, this would be 17 minus 10 minus 2 equals 5. The independent float is defined as the earliest time for event j minus the latest time for event I minus the duration of the activity. So in the example here, this would be 14 minus 11 minus 2, which would be 1. If this calculation should lead to a negative value, then we just take the value as 0. Interfering float is total float minus independent float. 5 minus 1 equals 4 in this example. In real-life building projects, cascade charts are often used to show more clearly which activities should be taking place at which times. It may be useful to highlight the critical path on a cascade chart. From a cascade chart, it is easy to see how many people are being used at a particular time on the project. We can therefore produce a resource histogram which shows exactly this, how many people are being used at any one time. Now, in this diagram, we can see that 3 people are being used at the most on this project. However, it may actually be a little bit more cost effective to only have 2 people working on the project and have it finishing a little later. This is known as resource leveling. Returning now to the original question of completing the critical path diagram for a project, it is sometimes necessary to use dummy activities. These are imaginary activities of duration 0 and are used in 2 main circumstances. One such circumstance is to express the correct order of precedence between activities. In this example, y is preceded by x and w, but z is preceded by w alone. A dummy activity will be needed in order to correctly express this on the diagram. It is fairly straightforward to draw the diagram so that v precedes x and so that w precedes z. However, we wish to add y to the diagram so that it is preceded by both x and w without implying that x precedes z. This is possible with the dummy activity, shown with a red dotted line here. We are showing that x and w precede y, but because the dummy activity has direction to it, we are not implying that x precedes z, merely showing that w precedes z only. The other reason to use dummies is to avoid ambiguity in our critical path diagram. We should never really have 2 nodes joined by a single pair of arcs. In this section of a diagram, for example, it is unclear whether the critical path should run through A or B. By adding a dummy activity, however, we can eliminate this ambiguity. If, for example, the 2 times at the end of the dummy activity here are the same, then we can see that the critical path must run through B, because if we trace a path through the nodes where the earliest and latest times are the same, this must pass through B. However, if these had been different, then the path traced out by nodes where the earliest and latest times were identical must pass through A and not B. Therefore, A would have been on the critical path instead.